Hi everyone, this is just a short video to try and showcase what you were supposed to do in the tutorial test to solve the problem on what I'm going to call a little bridge structure or beam structure supported by slanted columns. So basically what made this problem a bit out of the ordinary was that you were supposed to model the column as a truss element and the actual beam profile then for the deck as a continuous beam. Also there were some rotated supports and then the triangular load. So I'll get right into it. Basically you had to obviously sketch your schematization. I know this takes some time, but it shouldn't take more than literally 3 minutes. I think some of you might have spent too much time on actually drawing the sketch of the problem. Working out the area of your rectangular cross section for the beam also took a couple of minutes. I typically use MATLAB to do these little calculations. I'm not expecting you to use its solver like I've done here to get the answer, but I mean you can just write out the calculation and use MATLAB as a calculator as well. In any case, the A and B dimensions of the rectangular section were supposed to be 0.1633 and 0.24495. Right, back to Abaqus. Or maybe I should just flash the problem again. That was a little bridge structure. So we had 6 meter back span as they call it, and then a 12 meter central span with our 10 meter columns. So a bit of a quick calc to just work out that the height of the structure from base here is 8 meters. So 8 squared is 64, 6 squared is 36, which gives us 100. Square root of that is 10. Right, so I'm going to start off by creating a 2D planar wire part. Just for the sake of it, I'll call it bridge here. And the approximate size of this thing is about 20 meters in length. So if I continue, I'm going to start entering my coordinates. Now I'm going to choose to make this top node 1 at 0, 0. The reason I'm going to do this is because later on I want to define a rotated coordinate system at this point, and it's easiest if you're at 0, 0. So basically we go back to Abaqus. We're going to say we're going to start at 0, 0. We're going to go 6 meters to the right. That takes us to the support, and another 6 meters to 12, 0. That takes us to the center of the span. A second curve I'm going to define from then 0, negative 8 meters, and to the central support there. That's it. We say our section sketch is done. I'll go right over to the material. I'm going to define, we'll call it steel, and mechanical. We're going to do a less elastic material. Young's modulus of 210 gigapascal, 0.3 Poisson's ratio. Right, next thing, profiles. The top deck profile there, I said you should use a rectangular section. So I'm just going to call this beam. I've already told you that you can work this out very quickly using something like MATLAB's fsolve function. Basically the fsolve function takes a little script like this and it solves a nonlinear equation. Please don't have a hang up about using this. Doing it by hand shouldn't take more than a minute in any case. I'm just using it so I can copy the A value right into Abaqus here. So let's say paste the value there for A and the B dimension. If you work out something like this, it goes without saying, but you can just check that, for example, area in this case would be the first element of that one vector times the second element of 1, which obviously gives us back our area that we were supposed to have. Just double check your work as you go along. Second profile we define here in Abaqus would be the pipe profile. I'm going to call that my column. And I gave you the radius on the drawing of 0.06 and the thickness of 0.01. That's done. Define some sections. First one, you're going to have a section for the top deck area, it's beam. And so basically we're just going to select our profile there, and the material is already defined as steel. We only had one material in the model. Second section we need to define would be a truss actually for this column member. Eventually we're going to actually use this as a single element to model a truss element connecting to the deck there, so that we only have axial forces there. So basically if we do that, we need to give it our area. So again, back to MATLAB, pi times, let's be more than generic, I'll say d outer equals 0. Let's do radius, r outer equals 0.06, r inner equals 0.06 minus 0.01, and then we're going to do the area of the pipe is equal to pi times r outer squared minus pi times r inner squared. And sorry, that was a 0 I typed in there before. There we go with the area. I'm just going to copy that again and stick it in Abaqus right there. There we go. Next thing up, we want to obviously on our part assign our section properties. So I'm going to do the section assignment for the column first. I say that's our section 2. I forgot to rename it. Do that now. It's a truss element, it tells us. And then the next one over, we're going to do this top part beam. Remember to press shift to select both. And that's the beam element. Right, so both of them have been assigned. We can actually now go ahead and mesh this thing. On the meshing module, remember first you want to say, okay, element type we want to do for this column. We want to say it's going to be a truss element. Right, so at the bottom of that list we do truss. Okay, we can do top parts there as beam elements. Shear flexible is fine. I didn't actually specify what you needed to use. If I told you it's not a Timoshenko beam, you would have to go here to cubic formulation. So we're just going to stick with beam. That's it. Then obviously for a truss element, like we know, we don't need intermediate nodes there. So I'll just go to actually the seeding that edge. Right, I'm going to seed that edge using one element in that column. And then just going to go ahead and use the global seeds. No, sorry, I don't want to. The global seed won't override the local one. So for the approximate global size, we can use the default and say apply, and see that it actually sticks it in there. Just to make sure we can view our mesh in the part display option under the mesh tab, general data mesh. We can go show node labels or part related modules apply. Why isn't the train there? There we go. We switch that button on, it does show us our node. Okay, and then we should actually go ahead and mesh the part. There we go. One thing that's left to do obviously is we go back to our bridge part here. You'll see I forgot to add the orientation of the members. So we have to go to property. Say that we want to orientate our column, for example, in the first instance. It shows the tangent vector. We just accept that, and that shows us the vertical direction of our cross section. You can click OK there. Again, we can do the same for our two beam sections. Except that shows us the cross section. We say OK, just to make sure it's done. Right, so what I haven't done yet is define the assembly. I'm just going to create an instance of that part. We select the part here, we say okay, that's 100%, we only have one part. Next thing to do is to create a load step. So we create a step, I just call it load, static general, there we go. And then I will know also I want to see nodal forces for these line line elements. So in the output, I'm going to request here the forces that we see, these nodal forces in the beam section orientation. There we go. Okay, the complicated things are really now defining the load, triangular load here, and then rotated support there, and the other supports. Right, load first, we know it's a field variable we have to give it. It's got that triangular distribution. Flashback here is that we've got 14 kilonewtons per meter there. So 14,000 newtons per meter, and that length there is 12 meters. So what I'm going to do is say, let's just go and firstly say that in the fields list here we can do an analytical field. I'm just going to keep its default name. And then here we're basically going to define it. I'm going to give it a positive value. You have to remember that if you define a negative value here for the direction, you have to have a positive value in your load list actually. Get back to that. But basically what we're going to do is we're going to say that we have 14,000 newtons per meter divided by that 12 meter length. And we times that by our variable x. So that's the actual distance along the global x-axis. We don't need to define a local one in this case because it coincides on that. So we've defined the analytical field. Next up we can actually do the load. Right, so we do a line load. And it's obviously on the whole of that beam member. And it's in the global axis. We're not going to have a local axis there. And the component will be in the y direction, component 2, and then I'm going to say -1. Right, so we've already scaled the load in the analytical field variable, so it's just -1. Oh, sorry, I forgot to select the actual analytical field. Make sure not to make that mistake. So I go back there. You have to say here that you want the load to vary by analytical field. There we have our triangular load. Right, so the boundary conditions, next thing up, we want to have a rotated coordinate system there. Now typically you can go to your instance display and you'll see the coordinate system creation little buttons here. So we're going to do a create a datum coordinate system using 3 points. Now a rectangular coordinate system is required here, so we have the correct output of our reaction. And now it first asks you, where do you want to put the origin? So we're going to tell it at that node. And then it says define a point on the x-axis. Now if you don't have a point, you can just, because this is 0, 0, you can just use your coordinates. You know that the cos of 45 is 0.707, so we can go in the x direction, we go 0.707, and in the y direction we want to go down by the same amount, so we're going to go comma minus 0.707, and in the z direction we're just going to have 0. So we say enter there, you see it rotates at 45 degrees, but we still just need to tell it another point that sits on this plane. Now obviously we're doing a 2D problem, and Abaqus doesn't know that necessarily, so we're just going to click on any other point there and it gives us our new coordinate system. It's the only one we want. So our boundary conditions, we simply go, we define the first one saying it's a displacement rotation condition at this point we've just defined. If we say done, we can actually now select that coordinate system, the rotated one. In the local coordinate system, U2 is now the y direction. We're going to make that 0. The other one is free. It's a roller support. Another boundary condition, displacement rotation at the bottom here, at the bottom of this bar element, we go U1 and U2 is fixed. And then lastly, we create the symmetry one at the end here. I'm not going to use the symmetry shortcut menu. I'm just going to use normal displacement rotation. So we know at this node we want to have x displacements fixed and we want to have rotations fixed. It's different from the tutorial problem where we actually had a hinge there. In this case we want both fixed, so I'm just going to say done there. It's in the global coordinate system and you're going to fix the x direction displacement and the rotation. Right, that's everything. We've meshed our problem from Correct, we've assigned our sections. That's all going to work fine, and then I'm just going to create a job. I'm just going to give it the default name to save some time and submit it. So at least it says that it's completed successfully. If we have a look at the results, okay, so it shows us the hormesis stress as the first output. Basically, that's not what we want to see. That's why I've selected in the field output these nodal forces, because the bending moment is typically that one you want to see. Right, so it shows you the bending moment at the end of each of these beam nodes. Sometimes it's nice to just show it in the underformed shape. It's easier to sketch. There's two moments you wanted to have really to complete your sketch. In the sketch, I really just wanted to see the shape. Clearly, it's a non-linear moment. Non-linearity, slightly larger here where the larger part of the triangular node sits. And obviously, you want the moment at this node and the moment at the top there. Easiest way to do that is just to use this little peak function, probe values. My screen is a bit small here, but I can say select from viewport at the nodes. It's probably maybe easiest even to do it per element, because then you can select this element here and it shows you that the bigger moment on that element is 103 kilonewton meters, and the same on this side. Right, so obviously you could save this to a file, you could do loads of things with it, but the test actually just said draw the shape. So I would at this point just take my pen, write down these values. Again, the bigger value is the one of interest there at the midspan, and then draw your bending moment diagram. I'm not going to write it to file. I'm just going to cancel this input, or rather I can leave the window open even. Can't really make it much smaller. But what I'm going to do is, if you click there on field output, you can now go and you say, let's look at the stress in our column, or maybe reaction force to start. So we want to see the magnitude or the resultant. If I say OK there, it's going to clear this window. So just so we don't want to write those to a file. Again, we want to see this reaction at this node at the bottom. So that just gives us the correct value, 117 kilonewtons. Yeah, so it was newtons, 117 kilonewtons. Again, that's what you want. You only really need that reaction to calculate the stress in this member. But you could get the stress directly. So one way is to do it by hand. So you can say force divided by the area of your pipe section gives you that stress. So let's do that quick. Yeah, so 117,685. So the area is in there, so we have 117,685 divided by the area of our pipe section. Right, that gives us 34 megapascals. So we know this is not going to yield, it's clearly smaller than 355. The buckling load is another thing we needed to calculate. At this point you can use MATLAB quite effectively to do that again. I'll just, clearly we can end off by just calculating what that is at the end of the tutorial. But that was the essence of it. That was the whole problem really. If you can sketch, okay, I didn't show you the deflected shape, but that's the same thing really. Sometimes it's useful to plot it as symbols even, so you can see the deflected shape or the maximum vectors there. I think the primary one where I use this, just maybe to show you again where this thing was switched off, is this sort of contour option. So you can go here by show tick marks for line elements, and it shows you this plot of deformation. Now this is reaction force, so sorry, there we go. U2 deformation, that's what we want to see. More important thing is, because we use the thrust element there, you don't have any bending moments in this member. You can just verify that again by plotting nodal forces. So the correct answer to this problem is exactly treating this thing as having a hinge there. Now I know we talked, Charles, about creating hinges in various ways, but it's important to note, because this type of finite element used for the column doesn't actually have a rotational degree of freedom at the connection. no moment is transferred there. We don't have to create an artificial hinge. Right, the last thing, just to check which failure mode governs, I gave you the actual expression here for critical buckling load, or the Euler buckling load. Pi squared EI over L squared, right? So for our pipe section, we have to still work out the moment of inertia of a circle. Pi d to the 4th over 64. If you want to use that directly, that's for a circle, obviously. So again, we have to subtract two things. So just say, just to be consistent with the formula, d outer equals 0.12, d inner equals 0.12 minus 2 times 0.01, right? And then we're just going to say pi equals pi, this thing now, pi times d to the 4th. I keep forgetting myself. But obviously we want to say pi d outer to the power of 4. Just going to close that in brackets, divided by 64, oops, not 46, 64, minus pi times d inner to the power of 4 divided by 64. That's I. E, just as a variable in MATLAB, would be 210 e to the 9, so this is meters in Pascal. Right, back to this thing. Euler load pi squared EI over L squared. Right, so we have P critical equals pi squared times E times I divided by 100. Right, so this is Newton, right? So format short, just to display that again. Oh, it still does that. Probably format long. I mean, you can clearly see what the answer is, just so you don't make a mistake. Anyway, it's 109 kilonewtons. Alright, so clearly our column will buckle. And that's the final answer of this term. I hope that this video has been informative. I think the main thing is that you teach yourself to work a bit quicker. Knowing Abaqus well obviously helps to do that. I hope there will be another one soon.